This is good. All right. So you guys know that I post the videos, right? And you can always go and look and say, oh, they did that one. That can help me. So number one. Oh, okay. So we've got an object that has 59 electrons and 42 protons. So, and they ask us about the total charge of the system. All right. Well, what's something we know about electrons and protons? So they carry opposite charges, right? Electrons and protons have opposite types of charges. And I would say the big but after that you may, hopefully you remember from chemistry, but the same amount of charge. The same amount of charge. I know, calling that chemistry stuff. Opposite type charge, but same amount of charge. Let's see, is there anything else relevant? Oh, I might put in here one quanta, in case that's a good vocab word there. I'd say that's probably about all you would need for the Y there. Shows you completely grasp the depth of the problem. So, I want to know what's the total charge of the system. Well, I can take the charge brought to the system by the electrons, and I can add that to the charge brought to the system by the protons. But I know that each one carries the same amount, and they're opposite types. So I could also look at it as, well, for the first electron, it's canceled out by the first proton, second one, third, all the way up to the 42nd, right? So I don't need to look at, when I'm looking at the total, I really just need to look at the net, or the excess charge that's on it. So I don't really need to look at, okay, how much charge does 59 electrons bring, and how much do 42 protons bring? I just really need to look at how much does 17 electrons bring, because that's the excess or the unbalanced part of it. So to do that, let's see, so I have 17 electrons. Each has a charge of, each electron has a charge of e to the negative type of e. Oh, okay, so 17 times the charge on each one would be the total charge. So that'd be 17 times 1.60 times 10 to the minus 19th coulombs. Oh, I think I'm done. That was quick. And I got 2.72 times 10 to the negative 18 coulombs. And that would be, of course, negative, because they bring a negative type of charge. So, yay! All right, so looking at number 12, this is one of those that when we did the example problems, we did just a diagram for these. You might also need some words to accompany your diagram. You may not, but I did some of both. And so what is the wire acting like? The spring. So I think if you don't see that, you're gonna have a little bit of trouble. So I would put something. I'd show that the wire acts like a spring, and what happens when you apply a force to a spring? It stretches. So what can we say about like the more force we apply, the more it stretches? Yeah, the longer it stretches, the more it stretches, something like that. So I would put that. More force, more stretch. And then I would probably also include a diagram here. I drew my wire horizontally. You could draw it vertically, right? If you wanted to. And apply the force there. So there was a force back. Did give that force any name? Tension. So this is a force of tension. And then it changed its length x. And I probably would make it so that like this end was attached to a wall. So I think that shows good understanding also, but you need to realize that it's acting like a spring. Would you listen to? All right. So from our equation sheet, let's see, where's our equation? There it is. We need good old spring equation right there. What does the negative in that equation indicate? Opposite direction, right? So I'm not really worried about the direction in this one. I know I'm pulling on it, and therefore I'm applying spring force and the displacement are in opposite direction. But so I'm just gonna right away say, well, I'm not gonna worry about the vectors here, so I can drop the vector notation and drop the negative sign. So all that's having to do with is direction, right? And let's see. The force of my spring, if I look at my diagram, is the force pair with the tension. So that means the tension and the force of the spring are the same, right? Just opposite directions. So I have that, don't I? 4.4 newtons equals, I think it's K that I don't know. Yeah, K that I don't know. There's like a little ripple here in the middle of my screen. It's kind of weird. And then I need to know how much it stretches. Oh, that's the 43.5 centimeters. So what's that 11.5 meters? Where does that come into play? Yeah, so it doesn't matter? No. What's called a red herring. Anybody know the term? Just to pull you off the right track. Yep. So, but should I use centimeters? Meters. So 0.435, right? Meters. And then I just solve for K. And I get 10 newtons per meter. Yay! Alright, so number 2. The magnitude of the electric force between two charges separated by this. Are those charges going to be attracted or repulsed from each other? They are both positive. They're repulsed, right? Okay. So, number 2. So what affects the forces between two charges? Distance. Well, could you close that cabinet, you think? Thanks. So what happens let's say as the distance increases, what happens to the force? The force decreases. And we could even get really mathy, and we remember what type of rule it is or law? Inverse square law. Which means not only does it go down, it goes down really fast. Does it ever go away? No. What do you think, Lily? Does it ever go away? Does it ever go away? Excellent answer. What else affects the force? The amount of charge. So let's say as the charge goes up, what happens to the force? What does the force do? Goes up. And then we already said the other one, like charges repel. Now you could write that, or you could do a little diagram where you have a positive charge and a positive charge and show that they have repulsive forces. Which of those forces is going to be larger? They're going to be equal because they're a force pair. He's getting some good answers from the front row here. All right, let's grab our equation that describes the electric force, which is the one right here, electrostatic force. And, I think it's just a sub in. Now, what are we looking for? Oh, we're looking for the electrostatic force, which is nice. It's already arranged for that. So let's see. F equals K, which is 8.99 times 10 to the 9th Newton meter squared per coulomb squared over the two charges, 0.25 coulombs and 0.15 coulombs. Hey, they're already in our base units too. Cool. 5 coulombs, 0.15 coulombs over their separation, 0.89 meters. Oh, that's already in our base units too. Nice, no conversions needed even. And the rest is arithmetic, which I'm going to trust that you can do your arithmetic. There's not even algebra, so. Yay! Good old number 5. All right. So we got this point charge of negative 0.45. What's that little n in front of the coulomb mean? Not micro, but nano. Is there anywhere you can find the value of what the prefix nano means? It's on the form sheet. Nano is the one I find easy to remember because it means -9. Nano begins with the same letter as negative and 9. So I remember it, no. Nano, -9. So there's a negative charge fixed at the origin. Where must the electron be placed in order to have the electric force acting on it be exactly opposite its weight? Okay. So let's see. Is the electron going to be attracted to this charge or repulsed from this charge? Is the negative electron going to be attracted or repulsed from this negative charge? Repulsed. Thank you. So, now we got to use a little logic. I'm going to start with the diagram, then we'll put some words. So, we have our little fixed charge here, Q. And then we've got our electron someplace, and it's going to be repulsed by this. I'm going to put a little negative on there just to remind myself. Which way does the weight of the electron have to act? The weight of the electron. Well, let's think about you first. Which way does your weight have to act? Down. What do we mean by down? Center of the earth, right? So which way does the weight of the electron have to act? Down, towards the center of the earth. Come on, folks, you can do it. So, if the weight of the electron's acting down, and it's being repulsed from this negative charge, should the electron be above this charge or below this charge to have those in opposite directions? Let's try below, because that's the only answer I heard. So here's our electron. So its weight is going to act this way, and then the electrical forces, this one's going to be repulsed that way and repulsed this way. Did we end up with its weight and the electrical force acting in opposite directions? So, I hear a yes. So, the green arrow and the blue arrow are acting in opposite directions on the electron. No. What are they acting in? The same direction. So this is good. Does the electron go below the fixed charge? No. So we've eliminated half the possibilities. The other half is, well, no, we've eliminated one of the possibilities. Does your intuition tell you maybe it goes next to it? No. So let's try. What about above? Maybe above. Let's try above. So here's our electron again. Its weight we know is going to be down because it's got to be towards the center of the earth. And let's see. If it's repelled, oh, I gotta erase that force too, don't I? So if they're repelled, now are the two forces on the electron going in opposite directions? Yes. Success. Yay! There was much rejoicing. So we've got it positioned so I don't even need to say the electron has to be above the charge because I've shown that in my diagram, right? Let's see, we could probably label in our diagram that this, what do you want to call that? Let's call it Y, because it's in the Y direction. All right, the distance between the two particles. Everyone okay with that being called Y? Good. So, what influences the electric force? What do you have to understand to know how the electric force is created? Okay, how do the charges influence? How do the charges influence? I just couldn't hear you, sorry. Okay. Good. That's a good thing to have in there. Like charges repel. Good. What else? What else affects its electrical force? Maybe look back in your notes. Number 1 was very similar to this. So was number 2 that we just completed. So look and see if there's anything that we used in the Y there that was talking about what affected the electrical force between two charges. The distance. How does the distance affect it? More distance, less force. Good. So more distance is less, and I'm going to label it as electrostatic force. Yep, I don't even need the arrow. Anything else influence the amount of force between two charges? I'll give you a hint. There is one other factor besides, just the universe itself. Let's move on to gravity. We'll come back to electricity then, okay? That's a good idea. We also have this gravitational force. So what influences the gravitational force? Mass, okay, so how does it influence it? Okay, so more mass is more force gravitation. And what else? Okay, so more distance, less force gravitation. So remember, one of the things one of the reasons why we did electrostatic forces is the analogy that they're very similar to gravitational forces. So you as a class was just able to pick out two things that influence the gravitational force: mass and separation. And so let's go back to the electrical force. And so far we've listed the separation, the distance influences the force. Is there anything else that you can think of that might influence how much force between two charged bodies? Mass is a suggestion. Do we think the mass affects the charged bodies? No. What physical thing does? Charge. Folks, look back. If this isn't getting into your head or something, go back, do the reading, watch the videos again. Because if you're not getting that force between charged bodies is influenced by how much charge there is, you've missed a major point and you need to review. All right, use this as a big old hint. And if we're done doing problems, this can be the last problem we do. Because the participation right now is, I don't know if it's because you don't understand or because you're not motivated to participate. I don't know. I'm not reading you this morning well. So either huge amount of review needed, or you're just not motivated to participate, or something. I don't know. So we need to stop and reevaluate. All right. So we need to start with the fact that the total force on this is equal to 0. And we have two forces acting on our electron: negative gravitational force plus a positive electrical force or electrostatic force equals 0. Therefore, those two must be even. That's the whole key to this. And now it's just plugging into the equation. to give you a minute to try that on your own, and we'll see where people are, whether we need to do any further on this one. All right, so maybe we'll see how that works.